In today's lecture, we are starting with module 4 and it's part 1. Actually, we are going to discuss about reference sources, how we can create a reference current source or reference voltage source. In many analog circuit applications, we need to give some reference voltage or reference current source. Example, if we consider differential amplifier, we need to give a current source, right? A current source at the tail current source. Most of the property of our differential amplifier, its common mode rejection ratio, power supply rejection ratio, etc., will depend on the property of our this current source. If this current source have infinite resistance, we will get CMRR is infinity or the common mode gain to 0. We prove that one, okay. Okay, actually I think we didn't discuss, but in common mode ratio, to improve the mode ratio, we need to improve the resistance of this one, or we need to idealize this current source. And in an op-amp, in case of op-amp, it consists of large number of differential amplifiers. So we need to replicate this one, this current source, and for that we are using current mirror circuit. Okay, so if we consider a current mirror circuit, we know there is a reference current, and we mirror that on to the nearby. How many circuits we have? We mirror to that one. Here I forgot this one. Here we will mirror to the load value. Okay, load here, this is our reference. We can control the value of I load by designing the value of W by L of 2. Here it is W by L of 1. We can design the value of load current, and the purity or the stability of this load current is basically depend on this reference current source. So we can spend more concentration on this reference current source, and if we are able to generate an ideal current source, or we will call normally at it says golden current source. If we have one golden current source, we can create many replica of that on using our current mirror circuit. So in basic case, what are the factors depending on this property of this current source, and how we can mitigate that, that is we are going to discuss. What are the parameters that affecting the stability of this current source, and how we can stabilize this current source. Or similarly, we need sometimes we need a voltage source, how we can stabilize that voltage source. That's the concept of this module, first part. And basically we are going to discuss 3 topics only in this one, that is supply independent biasing, and temperature independent reference source, and band gap reference. Actually band gap reference is it's derived from temperature independent reference source itself. Okay, so we need to discuss these 3 topics, and we need to discuss some circuits which gave stable current source or stable voltage source. So what is the meaning of supply independent bias? So in this case, if we consider this current mirror circuit, if I reference is depending on VDD, if there is a change in VDD, we need to verify a delta VDD we are giving. What happened to this I reference? If the I reference is independent of the variation in the supply voltage, the main supply voltage, DC voltage, then we can tell this I reference is supply independent. Actually, we need to create a reference signal which is independent of the supply voltage. So first we will discuss that, and second one, if we consider these MOSFETs, okay, its resistance value is 1 by mu n COX W by L. Okay, so it is 1 by mu n COX W by L. Most of the case we know, all the parameters of a semiconductor device, mu n will be there. Actually mu n indicate in the mobility, and mobility of electron or hole will be there. For every circuit we know, we in SSD as well as VLSI circuits, we studied that mobility of any semiconductor device, it's depend on temperature. It's depend on temperature. At low temperature mobility will increase, and high temperature mobility will decrease. Decrease in the rate of T raised to minus 3 by 2. Here it is increase in the rate of T raised to plus 3 by 2. The this increase, this decrease and this increase will affect the parameter value, the resistance of this MOSFET. That may also vary the load current. Okay, so these two we need to handle. And in our syllabus or in our as per the textbook, we need to discuss only few circuits which is compensating the effect of power supply, as well as which is compensating the or temperature effect is compensated. Okay, that we will discuss. So first we will start with supply independent bias. Okay, in supply independent bias, we will basically we will study with our current mirror circuit itself. Here it is a current mirror circuit. Okay, it's simply a current mirror circuit, and I reference is the current source and diode connected configuration, and here I0 is proportional to, or I0 is proportional to I reference. If the dimensions is WL of 2, here the dimension is WL of 1, then we can write I out by I reference is equal to W by L of 2 divided by W by L of 1. For simplicity of analysis, we are assuming that device for M1 and M2 lambda equal to 0 and gamma equal to 0. There is no channel length modulation and body effect. In textbook also they consider the same. So how we can create this I reference? Okay, how we can create, how this I reference is created. Here is an example how the I reference is created. If we consider this is the reference creating circuit, I reference creating circuit. If we consider this loop, okay, this loop, we can write the value of I reference. Simply we can write it as VDD minus VGS of 1 divided by R1 plus the diode connected configuration resistance is 1 by GM. And we can neglect the value of VGS1 or VTH value. So the equation of I reference become, here it become VDD into VDD divided by R1 plus 1 by GM. Then we need to analyze. So equation is satisfied here also. Only the I reference we redefine. So what happened if we change this VDD to VDD plus delta VD? Then this equation also changes to VDD plus delta VD, which will increase the current in the circuit, and the change in I reference we can write it as delta VD divided by R1 plus 1 by GM1. That means here the reference current is depending on the power supply. Okay, it's depending on the power supply. So we need to discuss how we can solve this one. Okay, as per the discussion, we found that if we are able to create I reference which is dependent on I out itself, there is a feedback from I out to reference. That means I reference is depending on I out. Sorry, here I out is depending on I reference. We know if we give a feedback loop or a looping system such a way that I out or I reference will depend on I out also, then we can create an supply independent bias circuit. Here is a modified circuit for the same. Here is the modified circuit for the same. So here we give an I reference, okay, and here we have I out. This is our one of the current mirror, first current mirror. As per the feedback principle, we are creating another current mirror here, that is current mirror 2. Okay, current mirror 2, and here we are creating a current equation such a way that I reference is creating I out such a way that I out by I reference, so I out by I reference equal to a value of K, and here we are feeding back the same current to stabilize the I reference itself, here also we will get the same equation, and please note here it is a PMOS. Okay, here it is PMOS. Okay, here it is PMOS, and the dimensions are, here it is W by L of n, here it is W by L of n of W by Ln into K. Okay, here also it is K times, and here it is P times. So from I out to I reference, it's become 1 by K. So you will get a relation between I out and I reference. So in this circuit, even if the VDD, even if this VDD vary, it will not affect the I reference value, because I reference is feedbacked from I out itself. So if there is a change in I reference, that means I out also want to change. So due to the feedback mechanism, there is no direct linkage with the V reference. But there is a drawback in this circuit. In this circuit, we are unable to define the value of I reference and I out. At we switch on using VDD, if there are some current in I reference, a multiplied current is available in I out, but the value of I reference is not specified or not. We can't fix that value. For fixing that output current, so we need to modify this one. So here I am clearing this one. To modify that, we need to writing some equation. We are modifying that such a way that we are giving a resistance RS. Here it is RS. Okay, it's my mistake. It is RS, RS in M2, and we are adjusting the ratio of dimensions of P MOSFETs such a way that the dimensions of both the P MOSFETs are W by L of P and W by L of P. Okay, this is the actual structure to develop a supply independent current source, or it is called a uniquely defined I reference or reference current source. Uniquely defined means in this circuit we can design the value of, or we can define the value of actual reference current value. Okay, in the previous circuit the working is same or the principle is same, but there we can't fix or we can't uniquely specify what is the value of I reference. At the starting, what is the value of I reference it is receiving? It will circulate in this loop. Okay, so here in this circuit we can generate a formula what is the value of I reference. For that we need to analyze this circuit into two current mirrors. This one is circuit 1 and this one is circuit 2. So here we will take I out is here and I reference is here. So from that first circuit we will get I out by I reference, which is equal to W by L of P divided by W by L of P, which is equal to 1 itself, because the dimensions are same. Okay, and in second circuit if we consider the current mirror 2, the value of P, both the gate voltages of both the MOSFET M1 and M2 is considered, that two are not equal. The gate source voltage of M1 we can directly write, it is VGS1. Here the VP, this voltage is gate voltage plus some RS value is there. The value of RS, voltage across this RS is I out into RS. Okay, so we can write that VP, here we written VP equal to VGS1, and which is equal to this VGS2 plus this voltage across this RS, that is I out into RS. So we need to solve these two equations, that current equations of first half, this loop and this loop, I reference and I out, from this VGS value to find the unique value of current source or reference current source. So from this VGS we can define the current in that first MOSFET M1 as root of, or VGS1 is defined as root of 2I reference divided by mu n CoX W by L of n plus VTH. So this is derived from the drain current equation. We are assuming that both the transistors or all the transistors are in saturation. So in the second half, or it's become 2, here it is current is I out, so it's become to I out by mu n cox w by ln. Here on k is there extra because in this circuit only M2 have dimension w by l of n into k. A factor k will be there. Okay, so plus VTH plus I out RS will be there. So here we can relate I out and I reference. So and if we have I reference equal to I out, then we can substitute that value to the I reference and we will get these two equations. And here we can take these things are common. Okay, these things are common. Here only root k is there. So equation become 2I out mu n cox w by ln into 1 minus 1 by root k is equal to I out RS. Here one root I out is there. So it will cancel each other. And by solving that you will get the value of I out equal to 2 by mu n cox w by l of n into 1 by r square into 1 minus 1 by root of k the whole square. This is an actual reference current source. Reference current source. Which reference? It is supply independent. Okay, supply independent. And in this I out value or the I reference value is nothing but I out value or I reference value is nothing but it's we can define in terms of RS and the dimension parameter K and the dimension of first MOSFET or W by L of N itself. Okay, so the output current value or the reference current value is independent of supply in this circuit. Here just it is looping around these MOSFETs. And in this circuit also one drawback is there. Because of this looping, if we give some value k equal to 1 or due to some reason at this starting, if the current value is 0, that current is looping through this one. Okay, if we give a power supply to this circuit, sometimes the entire current through the circuit becomes 0. Then once the looping condition is satisfied, like I reference is 0 and I out is 0, that condition is satisfied, it cannot turn on or it cannot produce any current. To solve that, we need to modify this circuit also. So there that condition is called a startup problem. Okay, startup problem. To solve that, we are adding an extra MOSFET that is called M5. This M5 is added such a way that at the beginning, when we give VDD, this MOSFET switched on, and it will make sure that some current is going through this loop. After that, it will go to off. If a current flow starts, if a loop current, a finite current value is flowing through the loop, then this M5 want to go switch off condition. So here I am just connecting a MOSFET in this configuration. The configuration is such a way that there is a direct path from VDD, our supply, to ground. Okay, supply to ground through source gate terminal or gate source terminals of some of the MOSFETs. Okay, here, okay, some of the terminals, so gate source or source gate terminals of some of the MOSFET. If we analyze this circuit, we can reach from VDD to the source of M3 to gate, and here these two are connected, so these also gate, this is also a gate source of, here it is gate source of M5, and here also a gate, so gate source of M1. So all VGS, through only VGS we can connect to the ground. That is the implementation behind this M5. M5 is implemented such a way that there we established a connection from VDD to ground through gate source. And if the value of VDD is such a way that this VDD is greater than the threshold voltages of these three circuits together. So okay, if these three circuits together, VGS1 plus VGS3 plus VGS5, okay, these three together, then all these transistors must switch on. Okay, if VDD is greater than VGS1 plus VGS3 plus VGS of 5, and in VGS3 we are using modulus because it's a P MOSFET, then all three MOSFET must switch on. Then a current flow will start. Some current flow will start. Once the current flow is start, what happen? This loop will establish. Here it become I reference, and here it become I out. Some current is flowing through this one, means the same current want to flow through I out, and same current want to flow through this I reference. So some current flow is start, means a current in the loop is established, and we are able to create a current in the starting condition. And next, once the current is established, we need to switch off this M5, or after the need of, or after its job, M5 want to switch off. Okay, it want to switch off. Okay, it want to switch off such a way that if all the threshold voltages are overcome, then the overdriven voltage is created here. Okay, some overdriven voltages is created. VGS1 plus VGS3, its voltages increase. Then we need to make sure that VDD, after all on, VDD must less than VGS3 plus VGS1. It consists of some overdriven voltage also. Okay, and plus VTH of 5. For the VTH of 5, we need to design such a way that it will own the transistors. It will own the transistor. It will own the transistor M3, M5 and M1 once all are switched off. Once it is switched on, then that VTH condition will not satisfy, or this due to the overdriven voltage of M3 and M1, the M5 cannot reach its threshold voltage and it's go switched off. Only we are discussing that condition here. Okay, no other derivation is there. So that is a development of supply independent bias. And I think I can go to the next condition also, temperature independent reference, or I will create another session for the temperature independent reference. Thank you.